Transistor characteristics, common emitter configuration. Here the aim of our experiment is to plot the input and output characteristics of a transistor in common emitter configuration, and hence to find the input resistance and the output resistance and the amplification factor beta. So here we are provided with an NBN BC107 transistor. Now this is an NBN BC107 transistor. The transistor is provided with the leads emitter, base and collector. We can very easily find out because the emitter side there is a small spot or dot is there. Then we are reading emitter, base and collector. Here for the purpose of giving connections, we have connected, or I have connected 3 wires to the 3 leads emitter, base and collector. Here the blue one is the emitter and base is the yellow one here, and the green wire is used for the collector. So emitter blue and the base is yellow and the collector one is green wire. Now we are provided with a voltage source for the input side and a rheostat, that is a potential divider arrangement. So in order to give the input voltage, and in order to measure the input voltage, a voltmeter V1 and a micrometer A1 is used. Similarly, for the output side we are having a voltage source that can provide a high voltage. With the help of a rheostat, a potential divider arrangement is there. Then to measure the value of the output voltage, a voltmeter VCB is used, and then another millimeter A2 is used to measure the current in the output side. Now let us discuss the theory involved in the transistor characteristics, common emitter configuration. Our aim is to draw the input and output characteristics. Now the input characteristics of a common emitter configuration is defined. The curve, this is the curve between the base current IB and the base emitter voltage VBE. The curve between base current IB and base emitter voltage VBE at constant collector emitter voltage VC. Now from that curve we can find the input resistance, which is the ratio of the base emitter change in base emitter voltage to the change in base current, delta IB. So delta VBE by delta IB at constant value of VCE, and that is obtained from the input characteristics. Similarly, the output characteristics is the curve plotted between the collector current IC, and the collector emitter voltage VCE, at constant base current IB. Now from the output characteristics we can find the output resistance as the ratio of change in collector emitter voltage to the collector current at constant value of IB. So delta VCE by delta IC at constant value of IB. Now the current amplification factor beta is the ratio of change in collector current to the change in base current IB at constant VC. So that is also obtained from the output characteristic, which is plotted at a constant value of VC. Now coming to the procedure part of the common emitter configuration. Now this is the circuit diagram that we are using. Now the emitter is common here. So the emitter is grounded. Now we are having the input side. This is the input side, and this should be the output side. And in the input side we have to apply a voltage between the base and the emitter, and that is base emitter voltage VBE. Now this base emitter voltage is provided with the help of a 2-volt battery. The positive of the battery is connected to the base through a rheostat. It is connected to the base, and the other terminal is connected to the emitter. The negative of the battery is connected to the emitter. Now we are using a potential divider arrangement, that is a rheostat is connected here. So the voltage is connected to the 2 lower terminals of the rheostat. So when the rheostat, the upper terminal is moved, the voltage across the base and emitter can be varied. Now to measure the current that is flowing through the base, it is a micrometer is used, that is A1. The current is of the order of microamperes. And to measure the voltage between the base and emitter, we use a voltmeter V1 that measures the base emitter voltage. So that is about the input side. Now coming to the output side, now the collector and emitter, that is the output, it should be reverse biased. For that the collector is connected to the positive of a battery, a 12 volt battery through a rheostat, the top of the rheostat. The battery, the lower terminals of the battery is connected to the two terminals of the rheostat. Now, to measure the collector current, we are using another ammeter, that is A2, that is connected to the collector. And to measure the collector base voltage, the voltage between collector and collector and emitter. Now, this is not VCB, that is VCE. It is VCE here, the collector emitter voltage. So, V2 measures VCE. So, that is a circuit diagram. Now, to perform the experiment initially, now this value of VCE is maintained a constant. Say it is a constant at say 1 volt with the help of the rheostat RH2. Now, RH1 is changing such that VB is changing. So, for each value of VBE, find the value of IB, the base current. So, we are finding the value of base current for each value of VBE. Now, seeing that we can see the tabular column, VC is kept constant 1 volt, VBE we are changing, then IB is determined or IB is find out. Then we can repeat the experiment. Now, we are changing the value of VCE to another value, say 2 volt, that is output voltage, remains a constant. Change the base emitter voltage. So, for each value of base emitter voltage, find the value of IB. Again, it is repeated for another value of VCE, keep the VCE value at 3 volt, find the value, change the value of VBE, base emitter voltage, and for each value of base emitter voltage, find the value of the base current. And then we can plot a graph, a curve. Now, this is the curve. Now, for 1 volt, this is the first one. For 1 volt, when a curve is plotted, that is VCE is equal to 1 volt, VB is plotted along the x-axis and IB is plotted along the y-axis. So, IB and VBE curve for 1 volt. So, that is the first curve. Now, the second one is the curve plotted for 2 volt, VCE is 2 volt. The curve is plotted between IB and VBE. Then again, third one is plotted, VCE is at 3 volt, IB is plotted along y-axis and VB is plotted along the x-axis. Now, from the curve, from all the 3 curves, we can find the input resistance, that is VBE divided by IB. Now, VBE is AB divided by BC, that is reciprocal of the slope. AB divided by BC gives the value of the input resistance. VBE divided by IB, that is AB divided by BC gives the value of input resistance. Now, coming to the output characteristics. Now, we are going to the circuit diagram once again for the in order to plot the output characteristics. With the help of the rheostat RH1, the IB is kept constant. The base current is kept constant, say at 20 microampere or 30 microampere or 40 microampere, etc. Now, keeping IB a constant, change the value of VCB, change VCB. Now, for each value of VCB, find the value of IC. So, we are having a tabular column between IC and VCB. Now, you can draw a curve between IC and VCB, taking VCB along the x-axis and IC along the y-axis, that is plotted for a constant value of IB. Now, change this value of IB to another value, say 50 microampere. Change VCB and find IC, plot another curve. Again, for another value of IB, say 60 microampere, again change the value of VCB and find the value of IC. Now, we can plot the third curve. So, we can see the tabular column that we used. Now, IB is equal to 40 microampere, VCE we are changing, for each value of VCE we are obtaining IC value. Then for IB 50 microampere it is repeated, VCE we are changing, for VCE we are finding the value of IC. Again, for 60 microampere of IB we are repeating, VCE changing and IC we obtained. Then we plot a graph between VCE along the x-axis and the value of IC, that is IC we obtained here. Now, IC is plotted along the y-axis, IC. At constant value of IB, say IB is equal to 20, 40, 60, 100 microampere. So, we plotted a curve, first curve, when IB is equal to 20. Now, this is the first curve, the lower one. The first curve plotted between VCE and IC, VCE and IC, VCE along the x-axis and IC. So, the second curve is plotted at an IB value of say 40 microampere and the third one is plotted at an IB value of 60 and so on. So, this is the nature of curve. So when Vc is increased beyond a certain value, the IC value remains a constant, and initially there is a small increase in the value of IC. So that is a curve. Now from this curve we can find the output resistance, that is delta VCE divided by delta IC. Delta VCE here, delta VCE is AB, delta IC is BC. So AB divided by BC, for each curve we can find out. For each curve we can find out the value AB by BC, that gives the value of output resistance. Then the current gain of the transistor, that is beta, that is delta IC divided by delta IB, delta IC divided by delta IB. Now delta IC from the curve we can see that is equal to delta IC or it can be obtained Mn. This is Mn is delta IC. Now corresponding value of delta IB is here 100 minus 60, or the IB value at M minus IB value at N, that is delta IB. From that we can plot delta IC by, or we can find delta IC by delta IB. So we obtain the result: input resistance, output resistance, and the current gain. Now coming to the experimental setup of the common emitter configuration, we can see the diagram here. The emitter is common, the emitter is grounded, and this is the input side and this is the output side. Now the transistor, we are using an NB BC107 NBN transistor. Here we are having the transistor here. Here emitter, that is the blue one is the grounded, that is given to the common ground, and yellow one is the base. So we are starting from here, the base. From the base it is connected to the negative of the micrometer, base. Then from the positive it is connected to the top or the movable edge of the rheostat, that is this connection. Then a voltmeter is connected between the rheostat and the ground, a voltmeter is connected. Now we are having a voltage source here, Now the positive of the voltage source is connected to one of the lower terminal of the rheostat, and the other lower terminal of the rheostat is connected to the negative of the voltage source. So that is the connection in the input side. Now coming to the output side, we can see from the collector. Now the collector is green. The collector is connected to the negative of the ammeter A2. From the positive of the ammeter, it is connected to the positive of the voltmeter, and also to the top of the rheostat. It is connected, the top of the rheostat. Then in the output also there is a voltage source which is about 12 volt. Now the positive is connected to one of the lower terminal and the negative is connected to the other lower terminal. So that behaves like a potential divider arrangement. Now using the value RH2, this rheostat, we can change the output voltage, and similarly using the rheostat RH1 we can change the input voltage. Now first, initially, to draw the input curve or input characteristics, we want to change VBE, the base emitter voltage VBE, we want to change with the help of RH1, then find the value of the base current IB. So IB and VBE. Keeping the VCB a constant. Now we are keeping VCB at a constant value of voltage, say 1 volt. Now VCB is maintained. Now you can maintain VCB. Change this one rheostat. We can change the value VCB. Now change the value VCB and fix the value VCB to a value of say 1 volt. Now VCB is fixed at value of 1 volt. That means at constant output VCB is 1 volt. Now we are changing the input side. RH1 is changed. Now this rheostat is changed. Now we can change the rheostat. Now we are starting from say 0.1 volt. But remember, keep VCB at a constant value of voltage, that is 1 volt. Now for 0.1 volt in the input side, that is VBE, base emitter voltage, the base current is 0. Now I am changing the base emitter voltage is 0.2 volt. Again the base current is 0. When the base emitter voltage is 0.3, now it is 0.3, again it is 0 here. Now it is 0.4, again it is 0 here. When it is 0.5, Now the voltage here, you can see the voltage here 0.5 volt, again the current is 0 here. When the voltage is 0.6, again the current is almost 0 here. Now when the voltage in the input side is say 0.7, now it is 0.7 here. What happens that the IB starts, we are getting a particular value of IB. Now the IB is equal to 10 microampere. Remember, VCB should be a constant, that is 1 volt. Now VCB is 1 volt. Input voltage is, base emitter voltage is 0.7. Now IB start flowing, IB is equal to 10 microampere. Now we are changing this VEB to another value, say 0.76. Now IB becomes a value of say 21. When it is 0.76, IB becomes a value of 21. When this value of VEB becomes a value of 0.8, now 0.8. Now it is 0.8 here, that is VEB. Now IB becomes a value of say 35. It becomes a value of 35 here. Now again I am changing the value of VEB to a value of say 0.86. Now you can see the IB becomes a value of 50 microampere. For 0.8 VEB, IB became a value of 50 for 0.86. Now for 0.9, now I am keeping the value of input voltage 0.9, then IB becomes a value of 64. But throughout the experiment we see E should be 1 volt. Now we are repeating. Now we can change VCE to another value. Now we change VCE to a value of 2 volt. Change VCE to a value of 2 volt. Now VCE is 2 volt here, 2 volt. Now in the input side we are changing again back. Now for 0.1 volt, IB is equal to 0. For 0.2 volt, IB is equal to 0. For 0.3 volt, again IB is equal to 0. For 0.4 volt, IB is equal to 0. For 0.5 volt, IB is equal to 0. For 0.6 volt, again IB is equal to 0. And for 0.7 volt, now 0.7 volt. Now the IB starts flowing. Now the IB is equal to 11 milliampere. Now when VEB is equal to 0.7 volt, IB is equal to 11 milliampere. Now we want to change VEB to a value say 0.76. Now VEB is equal to 0.76. Then IB is equal to 24 microampere. Then when IB is equal to 0.8, now IB is equal to 38 microampere. When again IB is equal to say 0.9, now here it becomes a value of 68. IB is equal to 68. Now once again we can change the value of VCE to a value of say 3 volt. Now keep it at 3 volt. Now VCE is kept at 3 volt. Now again we are repeating, we are changing the value of the input voltage. VEB is changed. Now as the value of VEB is changed, now we can see when VEB is changed, the IB start flowing. So for different value of VEB, find the value of IB. Now IB is changing, IB is increasing and not the value of IB. So that is the input side. Now coming to the output side, the output curve, we want to change the value of VCE. So initially VCE is kept 0, then IB is kept fixed. For example, here IB is fixed at 40 microampere. So the output characteristics is the curve drawn between the output current IC and the output voltage VCE at constant input current. The input current is IB. Now I kept IB is equal to 40 microampere. IB is equal to 40 microampere. Now you change the value of VCE. Now VCE is equal to 0.2 volt. Now you can see the ammeter is reading IE. The IE is equal to nearly 10 milliampere. Okay, 10 milliampere. Now again you change. Now VCE is equal to say 0.4 volt. Now it is increased to a value of 14. Then 0.6 volt. Now it is becomes 17. Now 1 volt, it becomes 1 volt. Now it become a value of 18 here, 18 milliampere. Now increase 2 volt. Now it becomes almost a constant. The IC value remains a constant at 18 milliampere, even though we are changing the value of VCE. Now 5 volt, again 18 milliampere, 6 volt. So 6 volt, 5 volt, 6 volt, etc. The IC value is 18 milliampere. Now we can repeat that. For repeating, we are changing the input current. Now the input current is changed to value of say 50 microampere. The input value is changed to a value of 50 microampere. 50 microampere. Now you can change the value of collector emitter voltage. Now initially, now we are getting a value of say 18 here, 18, then increase to 1 volt, 1 volt, now it became a value of 20 milliampere here. Now it is 2 volt, again 20 milliampere, that means remains a constant now. Now 3 volt, again 20 milliampere, 4 volt, 20 milliampere, 5 volt, 20 milliampere. So it starts from 17 milliampere and it remains a constant at 20 milliampere for the value of VC. Now once again we are repeating, we are changing the value of the base current to a value of 60 here, 60, to a value of 60 microampere. Now you can change. Now you change the value of VC. 0.2. Now for 0.2 we are getting a value of say 18 milliampere. Then 0.3. Now it is 20 milliampere. Now for 1 volt, it becomes 22 milliampere. Then 2 volt. Now it become a constant here, 22 milliampere. Now for 3 volt, 22 milliampere. For 4 volt, again 22 milliampere. So it became a constant. It became a constant in the output side. For different value of VCE, the current is 22 milliampere. Now with the help of that two values, we can plot the output curve. Now coming to a sample set of readings that you obtain for the common emitter configuration, the input characteristics, it is plotted. Now we obtain VCE value kept constant at 1 volt. Now when VCE is 1 volt, we change the value of VBE. We already changed and we obtain the readings, IB value. Now up to 0.6 we obtain IB is equal to 0. Now when VB is equal to 0.7 we obtain IB value 6 microampere. For 0.76 IB is 21. For 0.8 IB is 32. For 0.86 IB 50 and so on. So using these two values we can plot the first curve of the input characteristics. First curve of the input characteristics. Now to draw the second curve, we kept the VC at 2 volt. Then VB is changed up to 0.6 volt. IB value is 0. When VB is equal to 0.68, IB becomes 5. When VB is 0.7, IB becomes 12. And when VB is 0.9, IB becomes 72 and so on. Then again VC is equal to 3 volt. VEB value is changed. When VB is equal to 0.68, IB is equal to 15. When VB is equal to 0.7, IB is equal to 18. When VB is equal to 0.8, IB is equal to 42 and so on. So with the help of these VEB and IB at a constant value of VC, we can plot the graph. Now this is the graph, common emitter input characteristics. The graph is plotted VC at 1 volt, VC at 2 volt and VC at 3 volt. So 3 curves are plotted. So for the lower one, VC at 1 volt, we are getting a graph curve like this. Now this is the nature of the curve. The 3 curves are plotted. Now from each curve we can find the value of the input resistance. Here input resistance is AB by BC, delta VBE divided by delta IC. So that is AB by BC. Now AB by BC is determined here. We obtain 3333 ohm. Now from another curve, from this curve also it is calculated, that is AB divided by BC for the second curve. That is also we obtain a value of 3848. So find the mean of these two, that is taken as the input resistance. Now similarly, to plot the output characteristics, the input side is kept constant. The input is kept constant at 40 microampere initially. Now the VCE, the output voltage, collector emitter voltage is changed. Now the collector current is changing. Now the change in collector current is very small. For 0.2 it is 11, for 0.4 it is 13, for 0.6 it becomes 16, and from 0.8 onwards what happens that the collector current remains a constant at 18 milliampere. Then when it is changed, IB is equal to 50 microampere, Initially the value of IC changes to 12, 14, 16, 4.2, 0.4, 0.6. When it becomes 0.8 and higher values, the IC value remains a constant. Then again one more set of reading we obtained, that is for IB is equal to 60 microampere. Now VC is changed and corresponding value of IC is obtained. Then we plot a graph, the output characteristics of the common emitter. Now we get the curve like this. We can see that IC remains a constant. So for different value of IB, for 40 microampere, 50 microampere and 60 microampere, the curve between VCE and IC is plotted. So initially there is a slight increase and thereafter it remains a constant. Now from the curve we can find the value of RO, the output resistance. Now here for the first curve, in the linear portion we obtain the resistance. Here we are finding the resistance, that is equal to delta VCE divided by delta IC, that is AB divided by BC. So that is AB divided by BC, that is 100 ohm, 100 ohm. Now we can find the value of beta, that is delta IC divided by delta IB. Now delta IC is here. Now this one is delta IC, this much delta IC. So the IC changes from 20 to 22. So delta IC is 2 microampere. So 2 microampere, 2 milliampere, it is milliampere. It is IC is in milliampere, 2 milliampere. Now corresponding change in the value of IB is, here IB is 50 microampere and here IB is 60 microampere. So the change in the value of IB is 60 minus 50, that is 10 microampere. So delta IB is 10 microampere. So we obtain beta as 2 into 10 to the power minus 3 divided by 10 into 10 to the power minus 6, that is 200. So that is value of beta. So the values are recorded here. The input resistance, that is average value 3589 ohm, and the output resistance is 100 ohm, and the current gain of the transistor is 200.